Good morning.
Good morning, sir.
Okay, let's resume our discussion. So, what were the points that we discussed in the last class?
So we talked about entropy, then cross entropy, then scale divergence.
Okay. We have discussed about cross entropy and KL divergence mainly to introduce how the loss function can be formulated in a classification framework, taking into account the information content to reach out the information content of the target PDF or the desired PDF given the estimated PDF or the predicted PDF at that instance. Okay, so we have seen how to make what are the expressions and how to use them for effective formulation of the loss function. Okay, so now for a couple of lectures, let us concentrate or let us discuss on how do we perform different computer vision tasks. And then subsequently, we will see how deep learning has enabled these computer vision tasks to be performed through a learning-based or layered-wise network with learning for computer vision. Okay, so first let us understand different computer vision tasks, how they were classically dealt, and what are the main aspects in designing a different computer vision algorithms. So we understand now the principles of computer vision algorithms. In process of this, we also understand how to extract features or the attributes from an image, okay, or an image batch. This is very important, as we discussed before. This is a very important aspect, because unless we have good attributes describing the images, it is not very easy to make a decision or to perform any higher level task. Okay, so inference and classification or even detection, tracking, these all can be considered as higher level vision tasks or higher level tasks. So to perform any higher level task, what is necessary is to have actually the basic feature extraction or the description of the data or images mainly, or the signals appropriately given or appropriately done. Hope this is clear. So now let's target this lecture or couple of lectures from now, more specifically on feature extraction. Subsequently, we will see how this feature extraction has been used in computer vision tasks. And then subsequently, we see how deep learning enables this. Okay, so what we are discussing is on feature extraction first. Now we are heading towards inference. So what we are describing is the image content. Okay, is there a person, is there a car, or what is the object, what are the objects in it, what's happening in that image? Okay, so we are trying to describe the image content. Okay, and this is the basic task. This we can consider in some sense mid-level task or low-level task. Okay, low-level vision task. And of course, this can also be low to mid-level. Okay, so for effective feature extraction, sometimes we may need some good, some kind of organization or other things. Okay, so it can also considered as low or mid-level. Then making what? Inference or computer vision. After we understand how feature extraction is done, then we discuss about different computer vision. Algorithms to make what? To make inference. From what? Inference from images or image content or sequence of images. Okay, so this is high level task. Then what do we do? Third step. So this is a sequence that we follow or we need to understand. What is the third step or the third part that we discuss is on advent of deep learning. For what? To perform computer vision tasks. Okay, this is what we discuss. Okay, so now let's come to the first point. So we want to do feature extraction. From images anyway. So do you have any clue on how do we do it? See, the problems here of different nature. See, in some of the problems, what happens is the whole image there may be a single object. Okay, the whole image. Then in that case, the problem may be simply classification or recognition. Can you tell an example for recognition of this nature?
Sir, animal recognition, animal classification.
Okay, so animal recognition do we do or animal classification? We are distinguishing between classification and recognition as well here. So can you distinguish? So animal classification do we do or recognition?
We can do both.
If single animal is there, we can do recognition, sir. If we have to separate two animals, classification.
Fine. See, usually what we want recognition, opt examples we have to give. Anyway, you can do either way. So if you have a pet animal, you can recognize also. But in general,
Iris recognition, fingerprint recognition.
Right. So here face. So if you want to be more specific on recognition, okay, what we say is face recognition, iris, fingerprint. Okay, these kind of recognitions. Okay. Right. Classification. Of course, you can pose both as one as this and other as this. Okay, here say cat, dog, person. We are not distinguishing which person it is. Okay, kind of. So this is the these are typical examples of classification. These are typical examples of recognition. Recognition where we want to specifically give an identity. Okay, here we just want to put into one of the class. Okay, so of course there are some problems which you can consider either this way or that way. Say handwritten recognition. If you consider our handwritten classification, you are putting the digits into one of the class. Okay, that you can consider as classification itself. Handwritten. So if based on handwriting, you want to know who is that has written, or signature verification. Okay, that you can put as a recognition task. So there is a like a thin boundary or a separating line, but however, you should be able to know the clear distinction in case when we would like to make. Okay, when we would like to pinpointedly tell, are we posing it as a recognition task? So we should be able to tell actually more specifically which are the examples or what's the corresponding task. So yeah, tell.
So how do we distinguish between recognition and classification? Like if I've handwritten digits, I need to recognize the digit first and then I need to classify it. So are they subset of each other or they are entirely?
Yeah, see, you can consider recognition as subset of classification, where here also you're putting into one of the class. Okay, the frameworks are also similar, but this comes based on the nature of usage of the algorithm. Say, for example, if I want to authenticate, or if I want to, in a class, if I want to make an attendance, what I do is a recognition. Okay, so by this is the attribute given to the functionality rather than the modality. So this you can consider is the modality and this is the functionality. But however, if we would like to just figure out based on the task, what we are now conveying is, say, whenever we have a particular object, okay, to be identified, okay, that we are considering as recognition. A class of objects to be categorized, that we are considering as classification.
Okay, sir. Thank
So for example, all faces, a face versus non-face, we can put as a classification problem.
Class.
Okay. Say if I give you image patch and then say there is a person or not, that's only my objective. In that case, I put as a classification problem. Car, dog, person, if I want to separate, that is also classification problem. But if I want to specifically find out, so where is this particular person? Where is this particular person? Is this face belongs to this particular person or not? We are saying it is a recognition.
Okay.
Yeah, in fact, in computer vision as well as in machine learning, unlike in information theory and probably some of the mathematics courses, the terminology is loosely used. So people use like loosely, and of course they by meaning they can be applied here and there. So that's where the fuzzy boundary has come because in their usage and other things. But I think you can also see the intuition of what we are discussing now, classification versus recognition.
Okay.
Yeah. Oh, fine. So this is one kind of problems where we have actually the whole image corresponds to one object, or we want to perform a particular task with a algorithm. So if we consider this is input, let it be an image or whatever, and there is a say algorithm or some method we are developing. Okay, through this method, the input in this case is the whole image, and hence if you want to perform feature extraction or if you want to perform any operation, okay, we have to perform on the whole image. Okay, not only on a particular region of the image. And then the whole image is classified to one of the category or make some inference, whatever. From the whole image, not from the patch of the image or from a part of the image. There are other kind of data where again there are images where you have actually a bigger image. Assume that just I am plotting with respect to this just to have a slight distinction in terms of understanding as well. So in this big image, you may have actually say the problems may be many. Detect where the face is, detect where the object is, track where the object from frame to frame. Okay, so here what are important are different regions of interest. Okay, so we want to see where a particular object is, that is object detection. So the problems under this is classification, as we mentioned. The type of typical problems of this nature are detection, where a face is, where an object is, where a particular whatever gun is, any particular object where it is, that is detection. Segmentation. Segmentation, of course, can be done on the whole image. Okay, you need to give class label for a whole image. But however, if you would like to segment only particular say part of the image, that comes under this kind of things. Okay, segmentation. More tracking, more closely tracking. Okay, and then other kind of tasks. So optical flow, 3D reconstruction, they lie in between. They are to be done for the whole image, but they are in slightly in different manner. Okay, and sometimes even regions are also of importance. So 3D reconstruction, I will write them slightly differently. So these are the other operations where actually the whole image, this importance may be the whole image and even some regions of image. Okay, here you need both. Okay, so now in this case, what we need to do is say, for example, if I want to say where the particular object is, for this region alone, I may wish to get the features. Okay, so of course I can get the features for the whole image, but when I make a decision, the decision effectively has to be in this region of interest, not necessarily on the whole image. So here analyzing by parts. or analyzing by regions of interest, etc., makes more sense. So in this case, what happens? Where to look for information is also important. In this, information is there everywhere. Okay, in the first case, you see information is there everywhere for performing a classification task or a recognition task and so on. But for detection task or tracking task and so on, the information is there only at a particular region of interest, and identifying that is also important. So where to look? Here there will be, say, this whole thing is what to look. When we want to perform feature extraction, okay, the feature extraction mainly here, what is feature extraction to be done is what to look. In what? In image. Okay, that is the feature extraction. Here, what do we mean by feature extraction? First question is where to look. You understand, right? Where to look means?
Look at the whole image or a region of interest.
Right. Where is your region of interest? That is the question. First question. Second question is what to look there. Okay. So this is the process of feature extraction. So here what to look, when we ask, what we are essentially saying, rather than describing the image like pixels, can I describe it better? That is the question I'm asking. Okay, rather than describing it like a big array or a matrix of intensities, can I describe it better? That is the question I'm asking here. When I'm asking where to look, what is the question I'm asking? I am trying to say, rather than looking at the whole image, can I pinpointedly say that you look at this region, you look at this region, you look at this region, and then say that here you have information, important information, around that you just search, or around that you extract the, you see what to look. That's all. You don't need to see what to look everywhere. You only need to look around where you identified that regions of interest are. Okay, and then look it. Because that is important, because say in this case, assume that the dimension may be, say, let us assume that 100 cross 100. Okay, and this image, the dimensions may be 1000 cross 1000. Okay, so sometimes 1024 cross 1024. 1 megapixel camera, if you take, okay, if you take the image of the scene, that will be 1024 cross 1024. When you want to recognize a particular fingerprint, when a face and so on, their dimensions usually are smaller. In fact, it will be much smaller than 100 cross 100. They may be, say, 28 cross 28, okay, and so on. Also 28 cross 28, or say 50 cross 50, or whatever. These are the typical dimensions when you want to see the whole image and extract features and perform a classification, recognition, and so on. But when you want to look at a bigger image and want to identify a particular regions of interest and so on, there the dimensions will be, say, of the order of 1024 cross 1024, or even bigger, or slightly 512 cross 512, and so on. What, not 256 cross 256, even that is bigger. Okay, so there it is not good to see everywhere. You have to first pinpointedly say that this is where we want to look, and then we have to look for what information we need. Hope this is clear. Right? Okay, so now let's start. So feature extraction and whole image. If you want to perform, what kind of features do you suggest? Any suggestion on what features do you recommend when we want to perform feature extraction on the whole image? Yeah, give the features that you know. Assume that you have the whole image now here. Okay, assume that there is a, say, 30 cross 30 image. Okay, and then the intensities here, they vary in the range 0 to 255. Let this be I of x comma y. Okay, and then x and y is here. So based on notation, you can consider this as y, or this as x, or it's vice versa. So different books will consider differently. So anyway, for time being, I have just written x and y like this. Okay, some books it's more convenient to put x for many books, but I just put like this. to be familiar for you to go with the conventional notation. And then I of x comma y in the range I of x comma y is in the range 0 to f 255. Okay. So now given this information, what kind of features do you think we can extract from this image?
Pixels with high contrast difference.
Now, can you repeat? How do you do it? High contrast difference means?
So high contrast difference means like high intensity surrounded by very low intensity, which is easy to detect.
Okay, so can you give an example? Not understood fully.
So like in the case of edge detection, sir, difference between the intensities.
Okay. Fine. So that's okay. So you can say that this, you are saying essentially you want to enhance the contrast. Okay. Or you want to highlight where there are high contrast differences. Okay. Essentially what you are saying is if I have the whole image, okay. And then if there is a face image, okay. And then, so I assume that this, this is the face image. Okay. And then you want to highlight where you have actually the boundaries of this face. So that's what you wanted, correct? So
yes,
that's actually you are saying this one suggestion for that is say wherever the intensity changes, transition from say if this is I of x comma y at one location, okay, and at the next location I of x plus 1 comma y, okay, and then this difference I of x comma y minus I of x plus 1 comma y, okay, wherever this is high, this you would like to highlight essentially, right? Find the difference of x comma y in some sense in x direction, and that's what is this, and y direction also you can find same. Please note that all operations we are doing here are on 2 dimensions. It's not a 1-dimensional signal conventionally we know, or 1-dimensional sequence. It is a 2 dimensions. So whatever operation you do along x, okay, similar operation you have to do along y as well. Okay, please make a note of it. So along y also we perform the same. So assume that I of x comma y minus I of x comma y plus 1 or y minus 1. It's up to us how exactly we write. I plus 1 or I minus 1 or sorry, x plus 1 or x minus 1. Same here also. Okay, so if you consider this as the positive side, then it's you are doing like this. This is the negative side, you are doing like this. So this is actually, let's put x and y, right? Okay. So assume that you are performing this minus this and this minus this. So here anyway plus you are doing. Okay, later it doesn't matter. I will tell actually the how exactly we perform these things. But no need to bother too much on plus or minus here. Okay. Or you can assume that I of x plus 1 2 we are okay, fine. Let's be like this for time being. Okay, so this is what you are finding at each location, and you are highlighting some features now. So this is not purely feature extraction, you are highlighting features. So we can consider this also as a feature extraction. So this is by finding gradients in x and y directions. Gradients of what? This is gradient, discrete gradient. Those who know, okay, d by dx of I of x comma y, if you see, if it is a continuous thing, d by dx, it's a derivative. But equivalent of it in discrete case is I of x plus 1 comma y minus I of x comma y. Okay, this is also equivalent of this is I of x comma y. Any other way of writing gradient, discrete gradient? Any guess on how, what are the other ways in which we can write the discrete gradients? Instead of, I don't want to write f x plus 1 comma y minus I of x comma y, I want to define it slightly differently. Any other suggestions on how do I write the gradient? Discrete gradient in x. I of x minus 1 comma y. I can write like this, right? I can also define it as, okay, I of 2 times I of x comma y minus I of x plus 1 comma y minus I of x minus 1 comma y. Is this fine or not? I am defining different ways. These are all discrete gradients. What I am doing in one case, I am actually finding, say, if this is the middle pixel, okay, and these are the 2 pixels. What I am doing, I am adding these 2 and I am trying to see how much this middle pixel is different from the neighboring 2 neighboring pixels. That's why I have written 2 times of middle pixel minus the neighboring pixels. Otherwise, what I'm doing, I'm just simply taking what is the difference between this and this, or this and this. Okay, all things are correct. Discrete gradient is an approximation of the continuous gradient. You can do many different ways of approximation. Of course, you can also take more samples. You can see how this differs from all 4 samples, okay, in the neighborhood. Okay, similarly, you can do in the y direction. Hope this is all clear, what I'm discussing. If it is not clear, you have to ask. Okay, so gradients in x and y directions. This is essentially performed through edge detection. Or even more effectively performed through filtering by an edge operator. Okay, we will discuss or define those things. Those who know, I think it's fine. Okay, otherwise we will just pictorially show these things. Filtering means what? It can be like convolution. We will see later what is this all relation. This also helps us as the motivation of convolution neural networks. Okay, how does the convolution neural network has evolved? Also is based on the feature extraction, effective feature extraction, that we will highlight subsequently. Okay, so this is one way of identifying the features. Fine, good. So any other way? Any other inputs on effective feature extraction on the whole image? Yeah, I need some answers. Say I have whole image here, I have x comma y with the intensities 0 to 255, and I would like to extract features. So other than finding edges, no other features you can identify?
So depth.
Depth doesn't directly come, right? See, depth is a good feature, I agree. But how does depth directly come from images? We just want a basic feature extraction. That means we just want to have a first level of like describing an image or representing the image in a different way. Okay, that's what we are looking at.
But so I am a little bit confused. The feature extraction depend on the application. So what is
correct.
the application here? Like
very good.
Extracting edges. What?
Correct. Feature extraction depends upon application. Currently, what we are discussing is different possible ways of feature extraction. Later, we will pick from these set of possible feature extractions. Based on the application, I say that I don't want to use gradients. I want to use some other thing. Okay, I want to use say gradients in this application. So application wise, we will select which feature extraction procedure we want to follow. But we would like to list here a general procedures of feature extraction to get an idea of how in images feature extraction can be done. Yeah.
Okay.
Now, can some of you answer how exactly I do?
So when we were talking about depth, we can do it by the right shift and the left shift that we studied earlier.
Right. Correct. So when we especially look for depth, then right shift, left shift, and so on, we will see. So that we will see later. So that actually the algorithm itself has to take care, or even the gradients also are essentially doing, but we will see that little later. But now any other?
Isn't a feature?
No, it's not specifically a feature. See, you have to take left image, right image, and so on. We are now discussing on the whole image features. For a, say, assume that to be more specific, let's only I confine ourselves to classification and recognition task. Okay, in such cases, what are the kind of features we would like to look for? Rohit?
Yes, sir. Currently, what I is like edge detection. I've been thinking of a multiple ways also.
Okay, edge detection is done. That's conveyed. What else?
Yes, sir. Yes.
Corner detection.
Okay, very good. At least some other point raised. Good. So we are looking for feature extraction on whole image, but the point you mentioned is more important for feature extraction. Okay, at ROIs, region of interest. See, first of all, for this, what we have to do? First, we need to identify where the ROI is. Here, as we mentioned, the first question is where to look. So you need to identify at some point, say for example, if there is a object like this, okay, this corner may give a good information about the object. Because if I want to match this object across different images, or if I have some templates like this, okay, and I want to identify where this kind of templates are in an image. Okay, so or if I have assumed that if I have a car, okay, I want to find out where the cars are. Okay, I may wish to find out the corners. Okay, and based on that, I want to find out where around which I have to look for the information. Correct? So in such cases, what is important is identifying the corners of an image. Any idea on how do we do this? We just want to find a corner in an image, fine. How do you think we will do this? If I want to identify wherever the corners are, okay, how do we do this? Any idea on this? Any students can answer. See, corners are the points where there is a high intensity variation with respect to the whole neighborhood. So you see from corner point, okay, you move this side, or you move that side, or you move this side, there is an intensity change. In edges, what is that? The intensity change is only along the direction of edge. Okay, so if you move opposite to the direction of edge, there is a good intensity change. Along the direction of edge, if you move, okay, zero intensity change. Okay, along the direction of edge. Okay, you have actually zero intensity change, right? So, but whereas in case of corner, if you move in any direction, there is a good intensity change. So we should have again a methodology wherein we identify the intensity change in all directions. That also we do effectively. I right now write it, but later we will show it effectively through a convolution with a edge corner operator. Convolution or filtering, we will define all these things with a corner identifying operator. Okay, this will highlight. In fact, just to give an idea, this say x of x comma y, sorry, I of x comma y has to be quite different from what and what? From I of x plus 1 comma y So essentially what we are saying, I of x comma y has to be different from I of x plus 1 comma y. It also has to be different from x minus 1 comma y. It also has to be different from I of x comma y minus 1. It also has to be different from I of, okay, if we just consider these 4 surrounding pixels, okay, for this. Of course, you can also consider I plus 1, all these other pixels as well. So in that case, what happens? 4 times of this minus this has to be greater, okay, in some sense, for a corner, greater than some threshold, assume that. Then it is a corner. Okay, that's how it should be, right? So it has to be peak in the middle or it has to be dip in the middle compared to the surrounding pixels. Hope you got an idea of what I am discussing. Okay, so this is one kind of feature. This is more to answer where to look. Okay, this answers this. Okay, answer to this is this. Okay, right. So now tell me, around this point again, we may look for some features again. What features? Maybe edges or some other things. Okay, so any other idea on what features you know for the whole image? So
related to histogram, sir?
Yeah, it's histogram is a very good feature. So which we have been discussing for many computer vision tasks. See, it will also help actually the intensity distribution. So say, for example, there are some problems like red blood cells versus white blood cells, if you would like to classify. Okay, if we have an image with only one blood cell, we are somehow segmented and we have the color information in it, then histogram itself is a very good feature. So even say in many other tasks also, even for face recognition or face like human face versus a other object, dog for example, people use a histogram as the feature and then subsequently give it to the machine learning models. So if it may not be very like great feature, or it may not be able to solve the inference to the 100%, but it is also a good feature people use. Okay, and based on histogram, many other features which are very important and will help for computer vision tasks are built. Okay, so it's also an important feature. The next feature that is of importance is histogram. So what's an histogram? See, the why we are discussing this deep learning or computer vision task at the beginning, also to give you some domain idea about the task, or also about the applications or the problems at hand. Okay, how the computer can make inference on, and also since image processing is already dealt, whichever you know from that, don't hesitate to tell here. They directly get applied here. Okay, fine. So the next feature that is of importance is histogram. Okay, so what is histogram of an image? How do I represent a histogram of image, or what information does it has? What information does any histogram has?
Number of pixels at a particular intensity value.
A particular intensity?
Probability
Number
of a particular intensity occurring pixel.
Yeah, the frequency of occurrence of particular intensity in an image. Okay, and then here it is intensity. It may occur anywhere. It can be here. Okay, 0, for example, 0 can be here, 0 can be here, 0 can be here. So the frequency when we make, actually it's count of all wherever it may occur. Okay, so this also gives in fact a good understanding of the nature of image. So it also helps us to see is the image well taken. It also helps us the pre-processing. Pre-processing is also an important part in making inference. So if the image itself has very low contrast, what do we make out of it? First, we need to enhance it, right? And hence, even for that, or even as a feature, histogram has a good role. So this another advantage of this is this directly comes as a vector feature. So it is 255 cross 256 cross 1 vector. So and hence directly you can give it to a ML algorithm. So some of the tasks are effectively done through in this way. The other way of doing it is histogram can also be a feature in a when we want to look for the particular objects, okay, or different regions of interest. What we do in that case is we make the histogram for each different parts of the image. Okay, for this one histogram, and this is also another histogram. This is referred to as actually local histograms. Okay, and we concatenate and make the whole feature. Okay. And this also helps us say different processings are based on this. Say, for example, adaptive, if you would like to adaptively take different kind of attributes in different regions or different kind of processing at different regions, this local histograms will help. Fine. So these are the typical features. Any other features you want to name before we move on to the discussion on more specifically on the feature extraction?
Angle of edges.
Angle of edges, very good. Shape based features. A particular angle of edges. This what I have mentioned is the that is angle of gradient. Angle or orientation, right? Or angle of gradient. This leads to histogram of angle of histogram of orientation gradients. So this effectively what we do is, as I mentioned, so it can be, this is applicable both to whole image as well as for the local regions here, again at the regions of interest. This is histogram of orientation gradients, it is referred to as. What we do is at a given image, okay, so you can take actually a particular region wherever we are. So in this region, you find out all the edges. Okay, so you like whatever, whether it is a car or whatever, you find the angle of all these things. And then for this, you find a histogram. You make a histogram for this. So if you make a histogram for this effectively, so this will have actually, so in this histogram, at say this is 45 degrees, assume that this is 135 degrees and this is, say, for example, let this be 45 degrees. Let this be say 80 degrees. So this is 45 degrees, assume that this is 80 degrees and then this let be 135 degrees. Then what we'll have? We will have three peaks. Okay, at 45 degrees, at 85 degrees, and then at 135 degrees. Okay, so like this. Based on the number of pixels having that angle, you will have this magnitude of peak here. So this is actually 45 degrees. This is 80 degrees. This is 135 degrees. Okay, remaining you don't have in this patch. If you see, the histogram of orientation gradient essentially looks in this way. Hope you got some idea on this. This also will tell actually what kind of object we are looking for. If you see here, for this, if you just sketch the histogram of orientation gradients, how does it look like? 0 degrees, there is a big peak. Okay, and then this is roughly, assume that 45 degrees and then like this. So it's small, at all angles you have something, and then there's also some angles. So this may look something like this. Okay, so histogram of orientation gradients describes the feature information or the shape information in that region of interest and also is a good feature. Okay, see, along with this, as I mentioned, the gradient informations and then the corner informations and any uniform region informations, these are all done through filtering. So filtering also helps as a good feature extraction. Okay, so now in the next class, what we do is we will see how exactly we perform with some visual examples and inferences, how we perform feature extraction. Okay, and subsequently we will see where to look and what to look. And for that, we will try to give some answer. What to look is essentially feature extraction only. But where to look is essentially dealt in slightly different way that we will also see. Before I close, I just define, since filtering and the convolution, as I mentioned, is a good important process of extracting features, I would like to give a small inference on that and then we can leave. So hope all of you know what is convolution. Say assume that there is a signal, one-dimensional signal, just for simplicity. Okay. Now the question is, I want to find out high gradient regions or high contrast. Here high gradient in one dimension, right? So high gradient regions. How do I find it essentially? Any answer for this? So let this be with respect to the t. Okay, let it be continuous signal x of t. I just want to find wherever the high gradient regions are. Okay, how do I find? Any answer for that?
Differentiation.
Right. Okay, so now differentiation I want to do, fine, good. So differentiation of what? D by dt of x of t I do. Okay, I have done the differentiation, very good. So, and then what should I do?
Maximum of differential.
That's all. So you rather than maximum of differential, if this is greater than threshold, okay, then that, so at those locations, t star, where g of t is greater than threshold, all those t stars corresponds to high gradient regions. Correct? Now, in discrete case, how do you do it?
Forward or backward differentiation.
Right. So forward or backward differential, assume that x of n minus x of n minus 1 I want to see. Okay, and then wherever g of n greater than a threshold, okay, I say that it is a high gradient region. Okay. Now, what is the procedure of finding g of n, which is equal to x of n minus n effectively on the whole sequence now? Assume that I have a sequence now. Okay, in this sequence, I want to find now this g of n. How do I find it? What is the operation I should perform? G of n, let it be an output I want to get. Okay, and then I have x of n at my hand. What should be the system here? Okay, that gives me g of n. Any quick signal processing answer for this?
Delta of n minus delta of n.
Delta of n minus delta of n minus 1. So essentially what I'm doing, this h of n is called filter. What this filter is? Delta of n minus delta of n minus 1. Essentially, if you sketch this filter, it is like this. 1 here minus 1 here. This filter itself looks like ups and downs. Okay, that's why it highlights the ups and downs. Okay, and convolution with that filter will highlight the ups and downs, and threshold on that will give me only the high transition points. Let it be from negative to positive or positive to negative. Okay, so essentially filtering operation with an appropriate filter, extract the features of the filter. If you see filter has a gradient, you can extract gradient by filtering or convolution with that filter. Okay, this is referred to as filter or kernel. You design a kernel or filter like that, which feature you want to extract. With that, you can evolve. You get that feature out. Or use that, you get that feature highlighted. Is this point clear? If you have any questions on this, you can tell. What we are doing is this, we are sliding this filter. Okay, you are sliding on the whole image. And then seeing wherever the difference is high, that's what you are doing. So this multiple element wise multiplication with the samples and samples, sum them, and that's what you are showing as the output g of n. Okay, we'll show in more details in the next class. Okay, thank you then.